In this module, we're focusing on the critical area of attacks and exploits, specifically targeting specialized systems. We're now moving on to section 4.9, which involves explaining common attacks against these specialized systems. On this initial slide, we'll provide an overview of specialized system attacks. Understanding these attacks is paramount because different systems often have different vulnerabilities and attack vectors. This knowledge is crucial for effective penetration testing, allowing us to identify and mitigate potential threats more comprehensively. Let's move on to the next slide, where we'll delve into one particular type of attack: information disclosure in mobile devices. We'll define what information disclosure entails and its impact on mobile security. We'll also explore various techniques for extracting sensitive information from mobile devices, with a specific example of using Modbus, a popular tool for mobile app security analysis.
In our previous session, we introduced the concept of specialized system attacks and highlighted the importance of understanding these attacks within the scope of penetration testing. Now, let's dive into specific examples, starting with mobile attacks and information disclosure. In this slide, we focus on mobile attacks and specifically the issue of information disclosure. Information disclosure in mobile devices refers to the unintended exposure of sensitive data. This can have severe implications, including the leakage of personal information, corporate data breaches, and potential compliance violations. There are various techniques for extracting sensitive information from mobile devices. These can range from intercepting communication, accessing logs, analyzing memory, and reverse engineering applications. One effective tool for analyzing the security of mobile apps is Modbus, short for Mobile Security Framework. Modbus allows you to perform static and dynamic analysis of mobile applications to uncover vulnerabilities, including information disclosure issues. By using Modbus, penetration testers can identify and mitigate weaknesses that could lead to sensitive data being exposed. This ensures that the mobile applications are robust against such threats, helping to protect user information and adhere to security best practices. Next, we will delve into another critical aspect of mobile security: jailbreaking and rooting. We'll explore what it means, its impact, and methods for performing and detecting these processes, including a practical demonstration of using Frida for dynamic instrumentation. Let's move on to that topic.
Now that we've discussed information disclosure in mobile devices, let's move on to another critical topic in mobile security: jailbreak and rooting. So, what exactly are jailbreak and rooting? In essence, jailbreaking refers to removing software restrictions imposed by iOS, Apple's operating system, whereas rooting is the Android counterpart that allows users to gain root access and control over the device's entire operating system. While these actions can provide increased flexibility and customization for the user, they also open up significant vulnerabilities. The impact of jailbreaking or rooting a mobile device is substantial. It can undermine the device's security framework, making it easier for malicious actors to exploit vulnerabilities, install unverified applications, and manipulate system files. This can lead to data theft, compromised app integrity, and other severe security risks. Understanding the techniques used to perform and detect jailbreak or rooting is crucial for anyone involved in mobile security. There are various methods to jailbreak or root a device, ranging from software exploits to hardware manipulation. However, detecting whether a device has been tampered with can be more challenging and often involves monitoring specific system behaviors and configurations. A practical tool for working with jailbroken or rooted devices is Frida. Frida is an open-source dynamic instrumentation toolkit that allows you to inject scripts into running processes, making it an excellent choice for analyzing and understanding the tampering of mobile applications in real time. In the next slide, we'll talk about the abuse of permissions in mobile applications, which is another pervasive security issue. We'll use Drozer as a tool to demonstrate how to perform security assessments on Android apps regarding permission misuse.
Continuing from our previous discussion on jailbreak and rooting, we'll now shift our attention to another common mobile attack: permission abuse. In this slide, we'll first define what permission abuse is and discuss its impact on mobile applications. Essentially, permission abuse occurs when apps request more permissions than they actually need to function, or misuse the permissions they have been granted. This can lead to significant security and privacy risks, as malicious apps can gain access to sensitive user data or device functionalities. Next, we'll cover various techniques for analyzing and exploiting app permissions. Knowing how to examine granted permissions can help in identifying overprivileged apps and potential vectors for attacks. Finally, we'll illustrate this with an example using Drozer, a comprehensive security assessment framework for Android. Drozer facilitates testing the security posture of apps by identifying potential vulnerabilities and abuse of permissions. Stay tuned for the next slide, where we'll move from mobile-specific attacks to exploring AI-specific threats, particularly focusing on prompt injection attacks.
On the past slide, we discussed permission abuse in mobile apps, focusing on how excessive or incorrectly implemented permissions can be exploited, and we used Drozer as a practical tool for conducting security assessments on Android apps. Now let's delve into AI-related security concerns, specifically prompt injection attacks. Prompt injection is an emerging threat where attackers manipulate the input prompts of AI systems to influence their behavior in unintended ways. This can compromise the integrity and safety of AI-driven applications by injecting malicious commands or data, leading to potentially harmful outcomes. In this section, we'll explore various techniques for carrying out prompt injection attacks, and more importantly, how to defend against them. One common method involves crafting carefully tailored inputs that can mislead or deceive AI models, altering their responses to serve an attacker's goals. For instance, you might design a specific input that tricks an AI into divulging confidential information or making incorrect decisions. To put this into practical terms, we will look at some real-world examples where these techniques were employed, demonstrating how attackers can manipulate AI behavior through malicious inputs. In the next slide, we'll build on this foundation by examining another critical AI attack vector, model manipulation. We'll discuss how attackers can alter the underlying models themselves, using techniques like adversarial examples to further compromise AI systems.
AI model manipulation involves tampering with the AI's internal mechanisms to alter its outputs. This can lead to incorrect, biased, or even harmful results, drastically impacting the reliability and safety of AI systems. To engage in model manipulation, attackers often utilize adversarial examples. These are specially crafted inputs that cause the model to make errors. For instance, subtle modifications to an image might fool a facial recognition system into misidentifying individuals. On the defensive side, techniques such as robust model training and input validation are crucial to mitigate these threats. In the next slide, we'll shift our focus to OT systems and the concept of register manipulation. We'll cover how attackers exploit system registers and illustrate this with an example involving Scapy, a popular tool for crafting malicious packets. Now that we've covered AI attacks through model manipulation, let's move on to operational technology, OT attacks, specifically focusing on register manipulation in OT systems. In this slide, we address the definition and impact of register manipulation within operational technology. Register manipulation refers to the unauthorized changes made to the memory registers of a device or system. Such attacks can compromise the integrity and functionality of critical infrastructure, leading to severe operational and financial consequences. Next, we'll discuss various techniques used to perform register manipulation attacks. These can range from exploiting vulnerabilities in communication protocols to injecting malicious commands directly into the control registers of a system. An illustrative example of this is using Scapy, a powerful packet crafting tool, to generate and send malicious packets that target specific registers within OT systems. Scapy's flexibility and extensive libraries make it an ideal tool for creating custom attack packets designed to change the state of devices unexpectedly. In our next slide, we will delve into CAN bus attacks in automotive systems, their definition, impact, and ways to perform such attacks using tools like TCP Relay for analysis and exploitation.
In the previous slide, we explored the concept of register manipulation in operational technology (OT) systems. We delved into the definition and impact of such attacks, various techniques used to perform these attacks, and provided an example using Scapy to craft malicious packets. On this slide, we shift our focus to CAN bus attacks, which are particularly relevant in automotive systems. The CAN, Controller Area Network, bus is critical in automotive networks as it facilitates communication between different electronic components in a vehicle. First, we'll define what a CAN bus attack is and discuss its potential impact on automotive systems. Disrupting CAN bus communication can lead to significant failures in vehicle operations, posing both safety and security risks. Next, we will explore the techniques used to perform CAN bus attacks. These include message injection, message alteration, and denial of service (DOS) on the CAN bus. Understanding these techniques allows us to better protect against such attacks. Finally, we provide a practical example using a tool called TCP Relay to perform CAN bus analysis and attacks. TCP Relay can be used to manipulate and analyze CAN traffic, allowing us to understand and evaluate potential vulnerabilities in the system. Now let's move to the next slide, where we'll examine Modbus attacks in industrial control systems, including their definitions, impact, techniques, and practical analysis using Wireshark.
On slide 9, we delve into attacks on the Modbus protocol within industrial control systems. The Modbus protocol is widely used for connecting industrial electronic devices, transmitting data over serial lines and Ethernet networks. Attacks on Modbus can result in significant disruptions in industrial operations, leading to safety hazards, financial losses, and compromised data integrity. We will explore several techniques for performing Modbus attacks. This includes tactics for intercepting Modbus communications, injecting malicious commands, or replaying captured data to manipulate industrial processes. For a practical example, we'll focus on how Wireshark can be used to capture and analyze Modbus traffic. Wireshark is a powerful packet analysis tool that allows us to inspect the data packets exchanged over the network, identify vulnerabilities, and understand the nature of the communications. By leveraging Wireshark, attackers can gain insights into the Modbus protocol behaviors and exploit them to execute malicious activities. In the next slide, we will move on to discussing plaintext attacks in operational technology systems, examining how unencrypted traffic can expose sensitive information and the techniques used to exploit such vulnerabilities. As we move forward from discussing Modbus attacks, where we looked at capturing and analyzing Modbus traffic with Wireshark, let's now delve into plaintext attacks in operational technology, OT systems, on slide 10. Plaintext attacks occur when the data being transmitted across a network is not encrypted, leaving it vulnerable to interception and exploitation. In industrial control systems, the impact of such attacks can be severe, potentially leading to unauthorized access to sensitive information, manipulation of data, and even control over critical infrastructure. To perform plaintext attacks, attackers often leverage tools that can capture network traffic, such as Wireshark or TCPDump, to identify unencrypted data being exchanged. Once they have access to this data, they can analyze it to retrieve sensitive information such as passwords, configuration settings, or operational commands. For example, using Wireshark or another packet analysis tool, one can capture unencrypted traffic and then filter and inspect the data packets to uncover critical information that should ideally be protected by encryption. On the next slide, we will explore another critical type of OT attack, the replay attack. We will discuss its definition, impact on OT systems, techniques for execution, and provide a demonstration on capturing and replaying traffic using TCPDump.
On this slide, we delve into replay attacks within OT, operational technology systems. A replay attack occurs when an attacker captures data transmitted between devices and then retransmits it to produce an unauthorized effect. This type of attack can significantly disrupt OT environments by mimicking legitimate commands or communications to compromise system integrity. To conduct a replay attack, an adversary typically uses tools like TCPDump to capture network traffic. TCPDump is a powerful command-line packet analyzer that allows attackers to intercept and log traffic passing over a network. Once the data has been captured, it can be replayed to impersonate a legitimate device or user, often leading to unauthorized access or control over OT systems. For example, An attacker might capture the packets of a valid command being sent to an industrial control system. By replaying this traffic, they can repeatedly send the same command without authorization, potentially leading to system malfunctions or even physical damage. In the next slide, we will explore near-field communication, NFC attacks, where we will define NFC attacks, examine their impact, and discuss techniques for carrying them out, including practical examples using NFC tools.
On the previous slide, we discussed replay attacks in operational technology (OT) systems, covering the definition, techniques, and real-world example of capturing and replaying traffic using tools like TCPDump. Now, let's move on to another form of attack, specifically in the realm of near-field communication, or NFC. NFC attacks can be particularly concerning given the widespread use of NFC technology in various applications like contactless payments and access control systems. On this slide, we will define NFC attacks and examine their potential impacts. We'll also explore various techniques used to perform these attacks. For instance, tools specifically designed to interact with NFC devices can be leveraged to exploit vulnerabilities. We'll go through an example to illustrate how these tools can be used to interact with and potentially compromise NFC-enabled devices. In the next slide, we'll be discussing bluejacking, where we'll delve into its definition, the impact of such attacks, and the techniques involved. We will also see an example of how unsolicited messages can be sent to Bluetooth-enabled devices, demonstrating the ease and potential threats of bluejacking. In this slide, we'll be focusing on bluejacking. So, what is bluejacking? Bluejacking is an attack method where messages are sent to Bluetooth-enabled devices without the permission of the device owner. These unsolicited messages, often harmless in nature, can still be disruptive and intrusive. The impact of bluejacking may range from simple annoyances, such as receiving unexpected messages in a public space, to privacy concerns if the messages exploit vulnerabilities in the Bluetooth protocol. It's essential to understand these impacts to appreciate the importance of securing Bluetooth connections. Now let's talk about techniques for performing bluejacking attacks. Typically, attackers use Bluetooth-enabled devices with specially designed software to search for nearby Bluetooth devices in discoverable mode. Once a target device is identified, the tool sends unsolicited messages, such as text files or contact cards, to the target. For example, imagine you're in a crowded area, like a mall or an airport. An attacker could use a smartphone equipped with bluejacking software to send unsolicited advertising messages or even prank messages to the Bluetooth-enabled devices around them. In the next slide, we will cover radio frequency identification RFID attacks, where we'll discuss their definition, impacts, and techniques to perform such attacks, including using RFID tools to clone and manipulate RFID tags. On this slide, we're shifting our focus to radio frequency identification RFID attacks. To start, let's define what RFID attacks are and their potential impact. Essentially, RFID attacks exploit the way RFID tags and readers communicate, potentially leading to unauthorized data access or manipulation. The techniques used for executing RFID attacks vary. For example, attackers could use RFID cloning tools to replicate an RFID tag's unique identifier, effectively creating a duplicate tag. This could allow unauthorized access to secure areas or systems that rely on RFID technology for authentication. Another technique involves eavesdropping, where an attacker intercepts the communication between an RFID tag and its reader to steal sensitive information. To illustrate, consider using a handheld RFID scanner to clone an access badge. With the cloned badge, an attacker could gain entry to restricted areas or systems without detection. In the next slide, we'll delve into Bluetooth spamming, where we'll discuss its definition, its impact, the techniques involved, and provide a concrete example to further our understanding.
Building on our discussion of RFID attacks in the previous slide, let's now turn our attention to another vector of wireless communication vulnerabilities, Bluetooth spamming. In this slide, we define Bluetooth spamming as the practice of sending unsolicited messages or advertisements to Bluetooth-enabled devices within range. Just like email spam or SMS spam, Bluetooth spam can be annoying, invasive, and in some cases malicious. The impact of Bluetooth spamming can range from minor irritation for the recipient to potential security risks. For instance, Bluetooth spam messages may contain links leading to phishing sites or malware downloads. The techniques for performing Bluetooth spamming often involve scanning for nearby Bluetooth devices and then sending message payloads automatically once devices are detected. Attackers can use specialized software and hardware to conduct these spamming campaigns. An example of Bluetooth spamming is using a tool to send repeated spam messages to all Bluetooth-enabled devices within a specific area, like a crowded public space. This not only disrupts users, but can also be used to propagate malicious links. Now that we've covered RFID and Bluetooth spamming attack vectors, our next slide will look at the Scapy tool. Scapy is a powerful and versatile network manipulation tool, which can be used to craft and send packets for specialized system attacks. We will delve into an overview of Scapy, discuss some techniques for its use, and provide an example scenario.
Continuing from our discussion on Bluetooth spamming, let's delve into one of the essential tools for specialized system attacks, Scapy. Slide 16 focuses on the Scapy tool. Scapy is a powerful Python-based interactive packet manipulation program that allows us to create, modify, and analyze network packets. We'll start with a brief overview of what Scapy is and what it can do. Scapy is particularly valuable for crafting and sending packets, making it an indispensable tool for tasks such as network scanning, packet forging, and network probing. Next, we'll explore some techniques for using Scapy in specialized system attacks. Scapy's flexibility allows us to tailor packet construction for specific purposes, which is crucial in both offensive and defensive cybersecurity strategies. Finally, we'll look at a practical example of how to craft and send packets using Scapy. This will give you an idea of how you can utilize this tool in real-world scenarios, enabling you to perform complex network operations with relatively simple commands. In the next slide, we'll move on to discuss another significant tool, TCP Relay, and how it can be used for CAN bus attacks. Stay tuned for an overview of TCP Relay and an example setup for traffic analysis. Continuing from where we left off with Scapy, let's now turn our attention to TCP Relay on slide 17. TCP Relay is another essential tool in our arsenal, particularly useful for attacks on Controller Area Network (CAN) systems. First, we'll provide an overview of the TCP Relay tool. TCP Relay is designed to bridge and relay TCP traffic, making it highly effective for intercepting and modifying data transmissions on a network, including those in specialized systems like the CAN bus, often found in automotive and industrial settings. We'll explore specific techniques for utilizing TCP Relay in CAN bus attacks. This includes setting up the tool to capture and relay messages between CAN nodes, allowing us to analyze, modify, or inject custom messages into the network. To give you a practical understanding, we'll walk through an example of setting up TCP Relay for traffic analysis. This will involve configuring the tool to intercept traffic on a CAN network, enabling us to monitor the communication flow and identify potential vulnerabilities. Next, we'll be moving on to slide 18, where we'll cover Wireshark and TCPDump.
Continuing from our previous discussion on TCP Relay, let's now focus on two other critical tools for network analysis, Wireshark and TCPDump. Wireshark is a powerful open-source packet analyzer that allows you to capture and interactively browse the traffic running on a computer network. It provides deep visibility into network traffic, making it indispensable for diagnosing network issues, analyzing security problems, and learning more about network protocols. On the other hand, TCPDump is a command-line packet analyzer that's particularly useful for capturing network traffic quickly and with a minimal resource footprint. While TCPDump lacks the graphical interface of Wireshark, it is highly effective for scripting and automation. When it comes to operational technology, OT systems, and broader network attacks, both tools serve crucial roles. Wireshark can be employed to visually dissect complex traffic patterns and identify anomalies or malicious activity. TCPDump can be used to collect packets over extended periods and filter out specific traffic types for closer inspection. For example, to capture and analyze network traffic, you could use TCPDump to capture packets from a specific interface using a command like TCPDump-IEF0. You can then save the capture in a file format that Wireshark can open, using the -w flag followed by the file name.
Once you have your capture file, open it in Wireshark to take advantage of its detailed visualization and analysis features to investigate the traffic further. We'll proceed to our next tool, MobSF, to explore mobile app security analysis and how you can leverage it for both static and dynamic analysis. In the previous slide, we discussed the essential network analysis tools, Wireshark and TCPDump. We explored their functionalities, such as capturing and analyzing network traffic, which are crucial in operational technology, OT, and network security attacks. Now, let's transition to our current slide, which focuses on the mobile security framework, MobSF. MobSF is an open-source tool that provides comprehensive security analysis for mobile applications. It supports both static and dynamic analysis, making it a versatile choice for security professionals. Regarding techniques, MobSF can scan IPA, APK, and APX files to detect vulnerabilities, perform code analysis, and decompile applications to review the source code. It also facilitates dynamic analysis by running the app in an emulator to monitor runtime behavior. For example, using MobSF, you can upload a mobile app and receive a detailed report highlighting potential security issues, such as insecure data storage, improper cryptographic practices, and more. This allows developers and security analysts to identify and mitigate vulnerabilities before releasing the app. In the next slide, we'll delve into Frida, another powerful tool for mobile application security. Frida enables dynamic instrumentation and analysis, enhancing our ability to identify and exploit vulnerabilities in real time.
Building on our discussion of MobSF in the previous slide, we now turn our focus to another powerful tool in mobile security analysis, Frida. Frida is an exceptional dynamic instrumentation toolkit used primarily for debugging and analyzing the runtime behavior of mobile applications. Unlike MobSF, which focuses on both static and dynamic analysis, Frida specializes in dynamic instrumentation, allowing you to inject custom scripts into running processes to observe, modify, and interact with their behavior in real time. To effectively use Frida in mobile attacks, you're generally looking at two major techniques. The first is function hooking, where you intercept calls to specific functions within the app, allowing you to alter their behavior or collect useful information. The second is method tracing, which aids in understanding the sequence of function calls, shedding light on the internal workings of an app. As an example, you might use Frida to dynamically analyze an encrypted communication channel within a mobile application. By injecting a script that hooks into the functions responsible for encryption and decryption, you can capture sensitive data in its decrypted form, providing invaluable insights into potential security flaws. In the next slide, we'll dive into Drozer, another essential tool for Android security assessments, and explore how it can be used to analyze Android apps for vulnerabilities. Now that we've discussed Frida and its capabilities in dynamic instrumentation and analysis, let's move on to another powerful tool for Android security assessments, Drozer. On this slide, we'll be covering an overview of Drozer, a comprehensive tool suite for Android security assessments. Drozer allows security professionals to interact with Android devices to identify and exploit security vulnerabilities. It operates by taking advantage of both Android Debug Bridge, ADB, and custom-built modules that can probe Android apps for weaknesses. We will also delve into specific techniques for effectively using Drozer in your security assessments. These techniques can help you analyze Android apps, uncover misconfigurations, and identify potential security issues. Additionally, we will look at a practical example where Drozer is used to analyze Android applications for security vulnerabilities. This will provide you with a clear understanding of how Drozer can be applied in a real-world scenario to enhance the security posture of Android apps. In the next slide, we will discuss another crucial tool in mobile security testing, the Android Debug Bridge, or ADB. Through this tool, we'll explore how to connect and interact with Android devices for in-depth security evaluations. Let's proceed to understand the capabilities of ADB.
Slide 22, Tools. Android Debug. Continuing from our discussion on Drozer, we now move on to another critical tool in the Android security testing arsenal, the Android Debug Bridge, or ADB for short. This tool is essential for interacting with Android devices from your development machine. First, an overview. ADB is a versatile command line tool that allows you to communicate with an emulator instance or connected Android device. It provides a variety of functions, such as installing and debugging apps, accessing the Unix shell on a device, and viewing logs. When it comes to techniques for using ADB in mobile security testing, there are several key methods you should be familiar with. These include pulling and pushing files to and from the device, running shell commands to gather system information, and accessing restricted areas of the file system for deeper analysis. For instance, you can connect to an Android device using the command adb connect device IP if you're using a network, or simply adb devices to list connected devices via USB. Once connected, commands like adb shell allow you to explore the device's system, and adb pull can be used to extract files for local examination. In our example, we'll demonstrate connecting to an Android device and interacting with it using ADB commands to identify potential security vulnerabilities. We'll look at accessing application data, inspecting installed apps, and checking logcat outputs for debugging information. Next, we will summarize what we've learned about specialized system attack techniques and the tools like Drozer and ADB in our concluding slide. We'll also discuss the importance of practicing these techniques for effective penetration testing and suggest further steps for continued learning.
Slide 23 presents the conclusion and a review of the key concepts we have covered in this module. To summarize, we've discussed various specialized attack techniques and tools that are crucial for effective mobile security testing. From the utilization of the Android Debug Bridge, ADB, to more advanced methods, we've explored the practical aspects needed for thorough penetration testing. Remember, mastering these techniques is essential for anyone looking to succeed in the field of mobile security. Whether you are a beginner or an experienced tester, continuous practice and staying updated with the latest tools and methods will significantly enhance your skill set. As you move forward, consider diving deeper into each of the areas we've discussed. Continue to practice, experiment, and expand your knowledge through further learning opportunities. This will ensure you stay at the forefront of mobile security and are well prepared for any challenges you may face in the field.